On the notation of Maxwell field equations. Maxwell's equations are the cornerstone in electrodynamics. Despite the fact that these equations are more than 100 years old, they still are subject to changes in content or notation. To get an impression over the historical development of Maxwell's equations, the equation systems in different notations are summarized. Introduction. The complete set of the equations of James Clerk Maxwell are known in electrodynamics since 1865. These have been defined for 20 field variables. Later Oliver Heaviside and William Gibbs have transformed these equations into the today's most used notation with vectors. This has not been happened without background noise, then at that time many scientists, one of them has been Maxwell himself, was convinced that the correct notation for electrodynamics must be possible with quaternions and not with vectors. A century later Einstein introduced special relativity, and since then it was common to summarize Maxwell's equations with 4 vectors. The search at magnetic monopoles has not been coming to an end, since Dirac introduced a symmetric formulation of Maxwell's equations without using imaginary fields. But in this case the conclusion from the special theory of relativity, that the magnetic field originates from relative motion only, cannot be hold anymore. The non-symmetry in Maxwell's equations of the today's vector notation may have disturbed many scientists intuitively. What could be the reason? That they published an extended set of equations, which they sometime introduced for different applications. This essay summarizes the main different notation forms of Maxwell's equations. Maxwell's equations. The original equations. With the knowledge of fluid mechanics, Maxwell has introduced the following 8 equations to the electromagnetic fields. The right equations correspond with the original text, the left equations correspond with today's vector notation. This original equations do not strictly correspond to today's vector equations. The original equations, for example, contains the vector potential A, which today usually is eliminated. 3 Maxwell equations can be found quickly in the original set, together with Ohm's law, 1.6, the Faraday force, 1.4, and the continuity equation, 1.8, for a region containing charges. The original quaternion form of Maxwell's equations. In his treatise 16 of 1873, Maxwell has already modified his original equations of 1865. In addition, Maxwell tried to introduce the quaternion notation by writing down his results also in a quaternion form. However, he has never really calculated with quaternions but only uses either the scalar or the vector part of a quaternion in his equations. A general quaternion has a scalar, real, and a vector, imaginary, part. In the example below, A is the scalar part and IB plus JC plus KD is the vector part. Here A, B, C and D are real numbers and I, J, K are the so-called Hamiltonian unit vectors with the magnitude of 0,1. They fulfill the equations. And a nice presentation about the rotation capabilities of the Hamiltonian unit vectors in a three-dimensional Argand diagram was published by Goff. Now Maxwell has defined the field vectors, for example B equal B1I plus B2J plus B3K, as quaternions without scalar part and scalars as quaternions without vector part. In addition, he defined a quaternion operator without scalar part, which he used in his equations. Maxwell divided a single quaternion with two prefixes into a scalar and vector. This prefixes he defined according to the original Maxwell quaternion equations are now for isotrope media, no changes except fonts, normal letter equal scalar, capital letter equal quaternion without scalar. Beneath the new notation, the magnetic potential field W and the magnetic mass M was mentioned here the first time. By calculating the gradient of this magnetic potential field, it is possible to get the magnetic field, or in analogy the magnetostatic field. Maxwell has introduced this two new field variables into the force equation, 1.11. The reader may check that the equations above identical to the previous published equations, 1.1, bis, 1.7, except the continuity equation, 1.8, has this time be dropped. From the above notation it is clearly visible why the quaternion, despite the deep engagement for example of Professor Peter Guthrie Tait, did not succeed. Then the new introduced vector notation of Oliver Heaviside and Josiah Willard Gibbs was much easier to read and to use for most applications. It is very interesting that Maxwell's first formulation of a magnetic charge density and the related discussion about the possible existence of magnetic monopoles became forgotten for more than half a century, until in 1931 Paul-André Maurice Dirac again speculated about magnetic monopoles. Today's vector notation of Maxwell's equations. The nowadays most often used notation can be easily derived from the original equations of 1865. By inserting 1.1 in 1.3, it follows the known equation. Equation 1.4 contains the Faraday equation and the potential equation for the electric field. Together with the potential equation for the magnetic field, 1.2 follows with applying the rotation on both sides of 1.23. From 1.2 follows further with the divergence. The 6 Maxwell equations in today's notation are Faraday's law, Ampere's law, Coulomb's law, with E, electrical field strength volts per meter, H, magnetic field strength amperes per meter, D, electric displacement ampere seconds per square meter, B, magnetic induction volt seconds per square meter, J, electric current density amperes per square meter, E, electric permeability ampere seconds per voltmeters, M, magnetic permeability volt seconds per ampere meters. Please note that the Maxwell equation of today have become subset of the original equations, which in turn have got an expansion with the introduction of the magnetic induction, 1.31. Today traditionally not included in Maxwell's equations are Faraday's law and sometime also Ohm's law. Seldom the continuity equation, 1.8, is even mentioned. But this equation defines the conservation of charge. The electric and magnetic field strengths are interpreted as a physically existent force fields, which are able to describe forces between electric and magnetic poles. Maxwell has analog to fluid mechanics this force fields associated with 2 underlying potential fields, which are not shown anymore in the today's traditional vector notation. The force fields can be derived from the potential fields as with J, electric potential field volts, A, vector potential volt seconds per meter. For a very long time scientists are convinced that the potentials do not have any physical existence but merely are a mathematical construct. But an experiment suggested by Yakir Aharonov and David Bohm has shown that this is not true. There arises the question about the causality of the fields. Many reasons point out that the potentials J and A really are the cause of the force fields E and H, including the material equations, 1.30, and 1.31, and with consideration of Ohm's law. With S, specific electric conductivity 1 divided by ohm meters equal amperes divided by voltmeters. The Maxwell equations become for homogeneous and isotrope conditions, E equal constant, M equal constant. Real expansions of Maxwell's equations. The Hertz-Ansatz. Recently Thomas Phipps has shown that Heinrich Rudolf Hertz has suggested another possibility to adapt Maxwell's equations. During Hertz's life this was hardly criticized and his proposal was vastly forgotten after his death. Usually the differentials are partial derivative and not total derivatives as shown in the comparison, 1.1, to 1.8, between Maxwell's original equations and the today's vector notation. Now in the equations, 1.26, and 1.27, Hertz has substituted the partial derivatives with the total derivatives d. With this the Maxwell equations become invariant to the Galilei transformation. What with the entity? Becomes. Now the question arises about the meaning of the newly introduced velocity v. Hertz has interpreted this velocity as the absolute motion of ether elements. But if v is interpreted as relative velocity between charges, then Maxwell's equations are defined for the case V equals 0, hat can be interpreted that the test charge does not move in the observer's reference frame. Therefore Thomas Phipps explains this velocity as the velocity of a test charge relative to an observer. Consequently in equation 1.33, the partial derivatives has to be replaced with the total derivatives, 2. The invariance of 1.40 and 1.41 against a Galilei transformation for the case that no current densities J and no charges are present can easily be seen. For V equals 0, a relative to the observer's stationary charge, always Maxwell's equations will be the result. For a Galilei transformation is R equal RVT and T equal T. From which for all V the equations are valid. If the observer moves together with a test charge, this reduces again to the equations 1.45 and 1.46. The first Einstein postulate, that in an uniform moving system all physical laws take its simplest form independent of the velocity, is in the example above fulfilled. In each uniform moving reference frame the observer always measures, for example, the undamped wave equation. The Dirac ansatz. The non-symmetry in Maxwell's equation system always has motivated to extend the set of equations. The most famous extension has originated from Dirac, who suggested the following extension. Together with 1.51, this ansatz must lead to the postulation of magnetic monopoles, which until today never has been, absolutely certain, detected. As a consequence of this ansatz the force fields E and B are derived from potentials according to where F and C represent the complementary magnetic potentials. Therefore as another consequence there must exist two different kinds of photons, which interact in different ways with matter. Also this has until today never been observed. The Harmuth ansatz. Henning Harmuth and Konstantin Mayle have gone a step further and suggested new equations, which differ to the Dirac ansatz only in that point, that no source fields exists anymore. Harmuth has used this proposition to solve the problem of propagation of electromagnetic impulses in lossy media, impulses in media with low ohm dissipation, for the boundary conditions E equals 0 and H equals 0 for T0 pounds. With S, specific magnetic conductivity volts divided by ampere meters. In the interpretation of this ansatz Mayle has gone again a step further and declares the equations 1.54 to 1.57 to be valid in all cases, what says that there exist no kind of monopoles, whether electric nor magnetic. The alleged electric monopoles, charges, are then only secondary effects of electric and magnetic fields. From 1.54 to 1.57, Harmuth GL has derived the electric field equation 2 and has shown that this equation can be solved for a certain set of boundary conditions. The same equation, 1.58, is designated by Mayle as the fundamental field equation. The Munera-Guzman ansatz. Hector Munera and Octavio Guzman have proposed the following equations, WCT. With. From this follows Maxwell equations, 1.26, 1.29, as shown below. Faraday's law. Ampere's law. Coulomb's law. In this notation the current density J and the charge density R are not understood as electric only but merely as electromagnetic entities. With an analysis of Munera and Guzman it can be shown that beneath the electric scalar field also a non-trivial magnetic scalar field should exist. Imaginary expansions of Maxwell's equations. The notation in Minkowski space. In electrodynamics the relativistic notation is fully established. Because of the second Einsteinian postulate about the absolute constancy of the speed of light, therefore its independency of the speed of the light source or light detector, the four-dimensional notation has been developed. But the force field vectors E and H cannot be used for four vectors. But the potentials and the charge densities have been regarded as very optimal to formulate the electrodynamics in a compact form. If we first have an event vector, then it follows in Minkowski space the invariance of the four-dimensional length ds. And From this follows the four-dimensional velocity vector 2, which gives the four-dimensional current density, with the four-dimensional gradient operator. Follows with the continuity equation, 1.8, with the four-dimensional vector potential, and with the D'Alembert operator. Follows the relation. But then the possibility for a compact and easy calculation within the Minkowski space comes to an end. To include the electric and magnetic fields, the following definition is used to determine the electromagnetic field tensor. With two equations with the components of the field tensor, the four Maxwell equations can be derived. With the first equation, follows for an arbitrary combination of L, M, n to 1, 2, 3 the Maxwell equation, 1.29. And if one of the indices L, M, n is equal for it follows the Maxwell equation, 1.27. With the second equation, follow the non-homogeneous Maxwell equations, 1.26, and 1.28. Simple complex notation. One possibility to enhance the symmetry of Maxwell's equations offers the inclusion of imaginary numbers. Inaudible uses the imaginary axis only for the missing terms in Maxwell's equations. Thus they become. From this result an imaginary magnetic charge and an imaginary magnetic current density. In this notation the imaginary unit I is used for variables, which are not physically existent, i.e. are not measurable until now. Thus by using I in the equations above the missing variables are placed into an imaginary, non-existent, space I, x1, x2, x3. 8-dimensional, complex notation. Elizabeth Rauscher proposes a consequent expansion of the complex notation, so that for each field and for each charge density a real and an imaginary part is introduced. Then, when using a correct splitting of the terms, two complementary sets of Maxwell equations can be formulated. The real equations are: with an elimination of I on both sides we get for the imaginary parts. As used by Inaudible, also Rauscher uses the imaginary unit I to sort the physical existent variables from the physical non-existent ones. The imaginary quaternion notation. Another possibility is the mixture of quaternions and imaginary numbers, what has for example been done by Honig. With the vector potential and the current density. Follows with the operator. And with the Lorentz condition the Maxwell equations with. Actually this notation is very efficient. It is, for example, easily possible to formulate the Lorentz force or equations of the quantum electrodynamics with this notation. But now the imaginary unit I is not used to separate the observable variables from the non-existent ones. Interestingly, there does not exist one single real number at all. Each real number is associated either with the imaginary unit I or with the Hamilton units I, j and k. With some additional rules also this notation can be expanded to 8 dimensions. This should be presented in another paper. Closing remarks. Different notations to the Maxwell equations are presented. Depending on the application one or another notation can be very useful, but at the end the presented variety is not satisfactory. This variety can be a hint that the correct final form has not been found until now. Many discussions have been presented about the existence of magnetic monopoles. But either the electric field is only a subjective measuring caused by the relative motion between charges, as it is said by the special theory of relativity, or the magnetic force field can be derived from a scalar potential field. In the first case magnetic monopoles cannot exist, in the second case they can exist. Despite of extensive experiments no magnetic monopoles have been found until now. So we can conclude that no magnetic potential fields must be postulated and that the non-symmetry in Maxwell's equations still are correct. Proposals to enhance the symmetry with imaginary numbers are interesting but covers the danger that with the simple mathematical tool a symmetric formulation can be reached vastly, but that the physical models do become nebulous.